October 2024, Taylor, Texas. A construction manager walks the floor of the largest building in the state. No chips are being made. No machines are running. 5 years in, $50 billion committed, and the factory is silent. Samsung is building the most expensive chip factory in its history, right here in Texas, one of the most complex industrial projects in American history. And even before it produced a single chip, it is already facing serious problems. Because the future of artificial intelligence and the global economy depends on what happens inside this building. Today, I'm going to tell you why. To understand what's happening in Texas, you have to understand the decade that broke Samsung. A decade ago, Samsung was unstoppable, the world's second largest chip maker, the brains behind the first iPhones, Nvidia's early GPUs, and Tesla's first autopilot computer. For a brief moment, it looked like it might overtake TSMC. Then Apple left, handing your most sensitive chip designs to a company that competes directly against you in phones. It was an impossible arrangement. Apple moved everything to TSMC, a pure-play foundry that designs no consumer products, competes with none of its customers, and focuses solely on manufacturing chips at the highest precision. From there, Samsung's foundry business unraveled. Their 7-nanometer processes stumbled. Yields, the percentage of working chips per wafer, collapsed to around 40%. At that level, you're producing more scrap than product. Nvidia left, then Qualcomm, then Tesla. Each departure cost billions in revenue and the production data that teaches a factory how to improve. In 2021, Samsung did something nobody expected. Instead of retreating, they went further. They decided to rebuild their chip empire, not in Korea, in Texas. Taylor, a town of 15,000 people, 30 minutes northeast of Austin. Flat, geologically stable ground. The original plan was focused, $17 billion, 4-nanometer chips, production by 2024. Then the world changed. AI went from research project to economic force overnight. TSMC had Apple and Nvidia locked in at 3 nanometers and below. Samsung had no anchor customer at that scale, so they made a decision that sounded bold, but proved catastrophic. Scrap 4 nanometers and rebuild Taylor around 2 nanometers before a single wall had gone up. This wasn't an upgrade, it was a complete reinvention. New machines, a learning curve measured in years, not months. The $17 billion became $50 billion. The 2024 launch date disappeared. The city of Taylor eventually slashed Samsung's financial incentives as delays mounted, and the hardest part hadn't even started yet. Building a chip factory is like performing surgery at the atomic level. The Texas limestone beneath Taylor wasn't stable enough, so Samsung drove more than 20,000 piles 35 meters into bedrock, poured over 500,000 cubic meters of concrete, and built 5 concrete plants on site just to supply the job. The result? A floating foundation, physically decoupled from the earth, that absorbs every tremor before it reaches the production floor. Then water. The fab needs 15 million gallons per day, 5 times what the entire city of Taylor uses. Samsung built a dedicated reclamation plant, recovering 90% of every drop. Then air. Texas humidity destroys the chemical compounds used to pattern circuits. Filtration towers trap particles smaller than viruses. The clean room spans 10 football fields, one of the most controlled environments ever constructed. Then power. Texas runs its own isolated electrical grid, notoriously fragile. The 2021 winter storm left millions without power for days. A fab cannot tolerate a single millisecond of fluctuation. Samsung built 2 independent high-voltage lines, each with redundant backup. All of that, the concrete, water, air, power, was the easy part. The thing that truly makes or breaks a fab isn't infrastructure, it's knowledge. At 2 nanometers, the transistor itself changes shape. For only the second time in 70 years, electrons stop behaving like particles and begin propagating like waves. The solution is a new architecture called gate-all-around, horizontal silicon nanosheets, each just a few atoms thick, completely wrapped by the gate controlling them. Mastering this process depends on what the industry calls recipes, the precise timing of every chemical step, temperature profiles, and gas ratios that vary between rooms within a single factory. TSMC arrived in Arizona already knowing. They mastered 2 nanometers in Taiwan first, brought the engineers who built those recipes, and had Apple as a launch customer, a constant flow of real wafers to calibrate against from day one. Samsung arrived in Texas still figuring it out, cracking 2 nanometers simultaneously in 2 countries with no major customer providing production volume, no Apple, no Nvidia, no rhythm. Yield is what separates success from failure. TSMC runs at roughly 90%. Samsung's first 2 nanometers runs came in around 50%. That gap is not a minor setback. It is the difference between printing money and burning it. But here's where the story turns. Because right now, March 2026, something is finally moving in Taylor. The first EUV machines from ASML have arrived. Samsung has ordered dedicated pellicle systems, filters that prevent stray particles from destroying wafers at the 2 nanometer scale. You don't order pellicles for pilot tests. You order them when you're committing to production. Risk production is targeted for second quarter of 2026. Full-scale output by 2027. Capacity, 50,000 wafers per month. And behind all of it, Tesla, a $16.5 billion contract through 2033. Samsung will manufacture Tesla's AI 6 chip exclusively in Taylor. This chip will run Tesla's full self-driving system, its Optimus robots, and its AI training infrastructure. For Tesla, the logic is strategic. TSMC's 2 nanometer capacity is locked up by Apple and Nvidia. Taylor gives them their own dedicated fab, 30 minutes from headquarters. For Samsung, Tesla is the anchor customer they've needed since 2021. Taylor was supposed to be proof that America could rebuild what it lost, that the chip supply chain didn't have to run entirely through Taiwan. Instead, it became a lesson nobody wanted. You cannot buy 40 years of compounding expertise. TSMC leads because of an unbreakable flywheel. The best customers bring data and revenue, which fund R&D, which improve the process, which attract even better customers. The moment you compete with your customers, you lose them. Without them, the process never improves. But 2026 is different. The machines are arriving, yields are climbing, Tesla is committed. The US government has put $6.6 billion behind this factory, and TSMC's dominance has created an opening. Apple and Nvidia are consuming most of the world's 2 nanometer capacity, leaving everyone else on a wait list. The empty clean room from 2024 is being filled. Whether what comes out of it reshapes the global chip industry or confirms that America missed its window, we are about to find out. The wafers are coming.